IoT. It stands for the Internet of Things. But what is it really? IoT describes the things that are embedded with sensors and exchange data over the internet. It's pretty much everything you know, with the prefix smart added to it. Smartphone, smartwatch, smart fridge. And there are billions of them. But what makes IoT so smart? IoT devices collect a lot of data, and I mean a lot of it. In fact, some think that there will be more than 40 billion connected IoT devices, generating 80 zettabytes of data in 2025. That's 80 trillion gigabytes every year. That amount of data gives you, engineers, superpowers to make better models and services. But with great power comes great responsibilities. You will need to design robust, scalable systems that can handle petabytes of data per second, and I happen to know the database that can handle such load. To show you how to use it, we will create a sensor simulator app that generates random data and pushes it every 10 seconds to the database. That's just one sensor, but we can imagine scenarios to simulate multiple sensors by scaling up the app using multi-threading, Docker, or Kubernetes. Let me know in the comment section below if you would like to watch such a video. We first create a new folder sensor and initialize a Node.js app by running npm init-y. We move to the directory and install the project dependencies. We'll use the Cassandra driver to connect to the database, .env, moment, and casual to create random data. We'll create on the index.js file that will run the main function. We'll define a sensor class in model.js, so let's go ahead and do that. We'll use the casual package to define a random sensor. The define function takes a name and a callback function as an argument, which returns a sensor ID of type UUID and the field type. We're using random element function that takes an array, so let's define the array. We'll name it sensor types and give it values of temperature, pulse, location, and respiration. Let's not forget to add the array to the random element function. Let's now define the class sensor. We'll start by defining the constructor. We'll deconstruct casual.sensor that we just created to get a random sensor ID and type. Then we export the class. In our main function, we will first generate an array of 1 to 4 sensors. We will console log the newly created sensors, then pass the sensors to the run sensor data, which we will define in a second. We'll add a constant buffer interval, which describes in milliseconds how long I would like the sensor to accumulate data before pushing it to the database. In this case, we choose 5,000 milliseconds. Then we'll add a constant interval that describes how often I want to generate data. In this case, every 1 second. In run sensor data function, we'll add an infinite loop in which we add a constant measures, which will contain the generated data. We'll add another constant last using moment to keep track of time. We add another for loop where we check the elapsed time and we delay at each iteration by interval. We then push to the measures array a random measure for every sensor we created. For that, we'll use map to run through the sensor array and return a constant measure of type measure, which takes sensor ID, timestamp, and a value. We'll console log the new sensor measure. Let's implement the measure class. We'll just add a constructor which takes sensor ID, timestamp, and value as arguments that we add to the class fields. We'll also create a helper function, random sensor data, which takes a sensor as argument and returns a value based on the sensor type. Let's now export random sensor data. We'll need another helper function, delay, that returns a promise and set timeout to time. Now, let's connect the app to the ScyllaDB using Cassandra driver. We'll get the cluster's parameters from the environment variables. Then we define a constant client that is equal to a new instance of Cassandra.client. The client class take a config object as argument. So we need to add contact points, which is an array of nodes, an author provider that will use ScyllaDB username and password, the local data center, and finally a key space. We'll make sure to return clients and export getClient. We'll add one more function, insert query, that will help prepare queries regardless of the table. To use it, we just need to define table name and columns getters for both sensor and measure class. In index.js, we use getClient to create a client constant, then insert the generated sensors to the database. In run sensor data, we'll create a batch constant to prepare the queries for all measures generated during the buffer interval, then run client batch to execute multiple queries at the same time. Then we shut down the client. Finally, let's run the index.js file, and that's it. Click the like button if you like the video, and leave us a comment to tell us more about what you'd like to see in the future. Thanks again for watching, and I'll see you in the next one.